Let's start a lecture 3 radiation transmission. Yeah, and it's one because the content of this part is very important and much, so we need to do it. So this is the outline. So the first part is starting with the so-called Einstein AB coefficient approach. It's a very smart approach. Einstein always do something smart. He's good at writing a very simple equation and give you a very strong insight. And I will tell you what it is. And second is we'll introduce something called the transparency condition. What does transparent mean? Because the transparent, we can have a very scientific condition and tell you what it is. Then next week we do some easy carrier statistic under equilibrium, but since laser is operating under a very high injection current, so then we must evaluate the number of carriers and the position of Fermi level under high current injection, and we will learn what the scientists do probably 30 years ago, and that will be easier because probably currently now if you are doing relevant research, you have a simulation software, and they will just give you a direct position of Fermi level, but you don't know where it comes from. So this is still very insightful to know if we want to do that by hand, how can we do that? And build some relation between the position of Fermi level and the carrier. Okay, so the radiation transition has the three mechanisms, but later you will know there actually only one mechanism. So the first mechanism we learned is called absorption, or to be more precise or more accurate, it should be called stimulated absorption, because it must be absorbed under stimulation. But since this is kind of redundant, so we can still say it is called absorption. Absorption is that if you have a carrier under low level, and this carrier is coupling with the electromagnetic wave, then after it couple, the energy is transferred from optical energy to the electrical energy. So it goes up to a higher state. So the overall rate should be written as that. The occurrence rate, or the transmission rate of the electron from level 1 to level 2, we denoted R12, should be proportional to the number of carriers in the lower level. Also the number of photons in my count, so that will be a total rate. So we can say that the R12 should be proportional to N1. Second, we should also encounter that the R12 should be proportional to the number of photons. But the number of photons is the in the unit of energy. So R should be proportional to the electric field square, because that will be the energy. Since it is proportional, we don't know exactly what the constant is, so it's fine. So E21 should be R should be proportional to Fm squared. Alright, and after this the process, one photon will load, and one electron goes to the higher level. Second is the called stimulated emission. Stimulated emission is that if the photon is if the electron is at high level, then the electron will be stimulated and goes to back to the lower level and emit another photon with the same photon energy. So the rate of the downward transition we denoted R21 from level 2 to level 1 should be proportional to the electron density at the high level N2. That's sure. Then similarly, because it is also relevant to the incoming photon, so it is also proportional to the electrical field in your environment, or the so-called cavity. Alright, so R21 is proportional to N2 and proportional to Epsilon squared. And the photon increase. at least for one electron increase for one more photon. But if for certain distance, it will grow exponentially after solving a simple linear differential equation. Alright, the third mechanism is called spontaneous emission, RFP. Or to be more precisely, it's also a kind of stimulated emission. But it is still stimulated by zero level energy. What does zero level energy? Because in the quantum world, if you take the professor solid state physics or some class, you will say there's also no zero energy. The minimal energy will have something like a half of. For example, for a harmonic oscillator, the zero energy happens of half of h bar omega. So, in analogy of the cavity photon, there's actually no something called the zero energy. So, the spontaneous emission, if you digging deeper to see that with the full quantum mechanics formalism, we will say that the electron at a higher level is stimulated by something so-called vacuum field energy. But vacuum field energy is a background. So while you doing the statistic, you will subtract that and giving no net effect to the whole system. Then it giving another photon out. So in the perspective of the ray equation, it's also be proportional to the electron at a high level, or we call the level 2 N2. But however, because it doesn't involve the real photons in the cavity, so it's no more proportional to the H square. So we can write it down simply as a proportional constant times N2. Then after the spontaneous emission, the cavity will adding up one more photon with a random we can just say random with a random phase. You don't know what it is because it depends on time and space. It could be anything. It doesn't necessarily correlated with other pre-existing photons, so it's called a random phase. Simply we don't know what it is compared to other ones. So let's write down the three equations in consecutively. So the absorption rate R12 should be a proportional constant. We just call it D12. That means the constant corresponding to R12. And the times the N1 and times the W is the spectral density or the power density. Since we see that it should be proportional to the photon. And the photon energy is proportional to the total energy. Since we can divide it by so many number of photons. So we can also write it down. It is proportional to the spectral energy with a given frequency. Or the frequency that matches level 2 and level 1. So this is a spectral frequency with the corresponding wavelengths. Alright. So all the other things dumped into a constant for the B12, so we can write the equation directly without concerning too much things. Similarly, stimulated emission also is proportional to N2, and also proportional to the spectral density with such wavelength. Then we dump every possible thing into another constant called the B21, since it's the transition from level 2 to level 1. And third, the spontaneous emission RSP is only proportional to N2. It's not relevant to W anymore. And we also put the proportional constant as A to 1. Since according to the name, you see that probably Einstein already had some bias under his calculation. Since the absorption rate and the stimulation all use the letter B, and the spontaneous emission use the letter A. That means you already think probably these two are pretty similar. And this one is different from the other two. Okay, so let's see what the Einstein did afterward. So the trick of using a proportional constant to build up the equation is called the Einstein AB coefficient approach. Also a very strong invention of his. Alright. But since now we are considered about the semiconductor, we need to do some revision. The equation right here is only a two-level system, but semiconductor is not two-level, it's two-bit. So we need to express the N1 and the N2 as the function as the density of state. Alright. So from E2 to E1, that means you have a conduction band at this energy level from the E2 to DE. So the N2 will be the density of state of your conduction band times the probability of its occupancy. Since it's not 100% occupied, it will be none. So okay, so this is the level, the number of electrons will be occupying at the energy E2 to E2. It will be the number of the electrons from E2 to E2 plus DE. Alright. So now we can replace the original N2 with the density of state in the conduction band. Similarly, we also need to put the number of N1 in lower level to be density of state at the its valence band times the occupancy rate at the lower level than DE1 at the lower band. Alright. And then, because the Pauli exclusion principle, the transition from one level to another is 1-to-1. If you want to transit one electron to another state, that state must be vacant. The total number of states is not infinite. So it's not only to it's also proportional to the Fermi-Dirac distribution at the both state. So R21, that means this process has already some electron at the lower level. So the probability is F2. Oh, sorry, R12 from low to 1. So the lower level must have some electron, and the high level must be vacant. So it will be proportional to F1 times 1 minus F2. Similarly, for the stimulated emission, the initial state is at high level, so it must be occupied by some electron first. So it will be proportional to F2 times the lower level is vacant, so times 1 minus F1. So that's a first revision of the Einstein's AB coefficient to a semiconductor scenario. The second revision is that because the band is continuous and the transition must be vertical. So while you're counting a small level from DE2 and DE1, so DE2 plus DE1 is delta E21. And since the transition is vertical, so you cannot count a transition from this side to the other side, or from this side to other side. Although very close, but mathematically it is not reasonable. So since the recombination must happen in pairs, since you are counting for those only in vertical transition, that means under a small energy increment at the conduction band and the valence band, the total state of this small increment should be the same. That will be the more reasonable way to do the statistic. That means the whole process will be limited to the state with a lower DOS. Yeah, if there's no state upward, the density of state is very low, and you have a very high density of state at the valence band. That is not useful because there's no state upward. So you cannot just tie them together. That will be limited. So the right way or the reasonable way is to impose an additional statistical requirement that the low CDE2 should be low E1. And let me introduce an idea called the reduced density of state. It's just something like you learned in the senior high physics. When there's a two balls circulating each other, you will calculate something called the reduced mass. Now the concept is pretty similar. Since you don't want to involve the mass of two things, so you calculate something called the reduced mass to describe the system with one number. So we already assumed that the low CDE2 should be equal to low VDE1. That's for the small increment in valence band and conduction band. Then we assume that will be equal to the low R DE21. So DE21, that means the energy increment from the perspective of photon. The E21 is the photon energy that should match the transition from E2 to E1. Alright, so those numbers should be equal. Let's call it something should be ampere, number of pair of the available transition. Then, since DE21 should be DE2 plus DE1, then DE21 will be written as low R in the denominator. So DE21 is written as ampere divided by low R. Similarly, the DE2 should be written as ampere divided by low C. And the DE1 could be written as ampere divided by low V. So the reduced density of state could be expressed by this. It's the sum of the inverse. And you will see the number of low R will be dominated by the one with a smaller density of state. If the low C is much smaller, it will dominate the total number of these two. Then it dominated your final density of state. So the transition will be limited by the state with a lower density of state anyway. So that's the second revision of the statistic with Einstein's AV relation. Alright, so now we can write it down the equation as below after considering those things. R12 should be a proportional constant times the reduced density of state. That means the real possible combination of the transition matching the conduction band and the valence band. Then the lower state has to be occupied. Higher state should be vacant. So it's F1 times 1 minus F2. And the spectral density of this incoming photon. Alright, so the set, if probably you after this arrangement, they will grow some new constant. But we can all dump into a number we didn't know yet. We call it P12. So the equate number could be still written without many concerns. Second, similarly, the stimulated emission is written as R21, as B21, low R, but this is also the same spectral density of the photon, but it turns to F2 times 1 minus F1. And the spontaneous emission also, it becomes the A21 times low R times F2 because the electron should be a higher state. F2 times 1 minus F1. Alright. So let's equate each other. So that's before equating each other, we can see what the reduced density of state comes out in the 3D and the 2D case. Case 1, if we do the simple parabolic assumption, that's what we do. This lecture, we just approach the band edge as a simple parabolic, so its behavior is just like a free electrons, different mass. Alright, so the E2 becomes the EC plus H bar squared K squared divided by 2MB, similar as E1, but with the minus sign. The E21 is the E2 minus E1 is EC minus EB, so it's EG. And the H bar squared K squared divided by 2 plus the inverse of ME and the inverse of MH. So it could be written like this with something called the reduced mass. This is useful. This number is for the optical transition. While you are doing electrical conduction, we didn't require a reduced mass since you are only concerning the transport of electron or hole only. But while you are doing the pair transition between electron and the hole, they will give you another the effective mass, which is also defined by the effective mass of electron in the hole, according what kind of transition it is. If it is a transition between electron and heavy hole, then it is MHH, and the transition with ME and light hole, MLH, then the spin-orbital transition. Alright. So the origin for the case of a particle in the box, the density of state is derived with something like this. Then while you are counting the transition rate, we can just mimic the position with some replacement. First, we will replace the MD rho to be the reduced density of mass. Second, the E becomes the E21 divided by EG. Since you want to obtain the same format, you need to remove the band gap to the other side. So there will be E2 divided by EG. So replace the E as the E21 minus your band gap. So this is the density, real density of state you should obtain while calculating the transition rate. So it will be this part for the 3D case. What if happen if it is not a parabolic distribution, no more a simple parabolic? We can still evaluate its density of state, but luckily we did not encounter this case. So let's see what if we want to do it more rigorously. So the density of state is E21 E21 should be mapping back to what happens in the case space. So first you will have the density of state in case space, and then the density of state in with decay. Then the rho 1 over rho r will be divided by 1 over rho k, dE2 over dk. So as long as you have the slope at some stage. For example, if you are calculating, for example, if the transition is the band is something like this. This is the conduction band, and this is the valence band. And we'd like to know the transition rate from here to here. How to evaluate its real density of state. Since this part is deviating from the parabolic very much, so the original right one density of state is not correct. So 1 over the IR could be written over 1 divided by k with k to dk according to the equation here. Then the dE2 is the And the dE21 is dE2 divided by E1. So you only need to know the slope of your band gap at the local stage. You can calculate the dE2 over dk and the dE1 over dk at each band. Then the unknown value is rho of k. And the rho of k is fixed. For a 3D case, the rho of k, the density of k in k space, is k squared divided by pi squared. For a very thin 2D dimensional case, it is a constant. It's not constant. It's k divided by pi over dt. And for 1, it is 2 divided by pi dx dy. This is the minor y case. And the 0, no, you don't have the rho of k because it's a delta function. Okay, let's see how does the phi of k derive the heat. Let's consider a very big cubic semiconductor. The k in the arbitrary condition could be divided by 2k squared, ky squared, kd squared. And because this is the particle box, k must be the pi over d times the even integer. So the number of states of a sphere, probably you have to know here this the same thing as the other class like semiconductor. So let's take a review. So the 1 of half is because we only want to take the positive numbers. So the number of the volume of the sphere, you can only take the first octane. 第一卦线 you have a axis as nx, ny, and nz, and you draw a sphere within that. And since you can only take the n for the constant, so you can only take the first octane of the total volume. So half of the 1 times the sphere, the sphere volume in the k space times by 2. 2 is the spin up or spin down, because one state you have 2 spin. Okay, so this is the total volume of specific k sphere. And every pi over d cubic will have 1 state. So n over this is the total number of states in a sphere with the same k. Then phi of k is 1 over b divided by n over dk. This is the definition. So it will naturally become k squared pi squared. Alright. So if we do the same, we can build this equation. And we have EK relation. So this is an example, we still take a parabolic, but we can still do that if you assume it is other constant or something. Or you can also try it is cosine, the way is the same. You do that, phi d is phi k dk over d, as long as you have a specific EK relation. Then you find the dk over d and put it back. And the since of phi k is already given is k squared over pi. So you will get something like this in the form of k first. Then find the relation between E and the k and replace the k with E. Then you still get the same thing. Yeah. So this is an example how it works, because we know the case of the parabolic expression. But if it's not, you can still do the same procedure to find it. Okay, let's take a very short break.